3.2, symmetric parabolic motion. What I like a lot about topic 3.2 is that it brings in not only stuff from topic 2, but also topic 1, specifically the trigonometry in topic 1, specifically the motion using for free fall in topic 2, and it puts those both together. For symmetric parabolic motion, it is like if you had a ball that travels up and then comes down and that the up is equivalent symmetric to the down. That means the delta t going up is the same as the delta t going down, as is the delta s is the same going up, and the delta s is the same going down. Now, so it's relatively easy in that sense, except, of course, it's like a ball in soccer being kicked, or a field goal, right? If you just watch Carpenter beat Miami, or something like that, he kicked the ball at some sort of initial speed, v, and that's going to have both a vx component and a vy. Well, the vy component, that's what's under the influence of gravity. For the vx component, that's not under the influence of gravity, and as the projectile travels, that doesn't change without any air resistance or anything like that. So, with that in mind, we'll have to remember how to find components of vectors. But in this case, instead of being a displacement vector, or instead of being, a displacement vector, we'll look at it, with distances like meters. Well, we'll look at it as it's a velocity vector. But we still find the components, the x and y components, in the same way. Okay? So here's a little trig practice for that. Okay, so let's say a clown is launched from a cannon. From a cannon at 25 meters per second at an angle of 40 degrees. Okay. What are the x and y components for the initial velocity? Okay, well, we have 25 meters per second. We have an angle of 40 degrees. And v equals that. That v can be broken into a vx, an x component, and a vy. And if you look on the front of your reference table, you'll see that Rx equals R cosine theta, and Ry equals R sine theta. Because, of course, let's look at the x. If we take the cosine of the angle 40 degrees, that would look equal the adjacent, which is Vx, over the hypotenuse, which is 25 meters per second. So we can see that Vx, bring that up, is equal to 25 meters per second times the cosine of 40 degrees. That just gives us, making sure we're in degrees, 19.2 meters per second. That's our initial x speed. And that does not change while the clown is in the air. In the same way, you could come up with an equation for Vy, which is V sine theta, and that would be 25 meters per second times the sine of 40 degrees, which is 16.1 meters per second for our Vy. So we have a Vy of 16.1 and a Vx component of 19.2. Another way vectors come in is when you have, like, you're calculating the overall speed at a certain time during flight. So example, a baseball returns to the ground traveling forward at 30 meters per second. It's coming down and downward at 55 meters per second. What is the ball's final velocity? Well, let's look at this. We have both an x component of 30 meters per second. That's the forward. And we have a y component of 55 meters per second. And we can see, putting those two together, we'll get this overall v like that at some sort of angle, theta. Now, to find v, can you see what we'll use since x and y are at 90 degrees to each other? Right, the Pythagorean theorem. So v squared is equal to vx squared plus vy squared. So v squared equals 30 meters per second squared plus 55 meters per second squared. V squared equals 3,925 meters squared per second squared. And V equals the square root of that, or 62.6 meters per second. And yeah, it could be positive or negative. We'll use the angle to define direction, though. And since we have the opposite of the angle and the adjacent, we can use a tan inverse of 55 over 30. This will give me a positive value because I use positive 55, even though it's really going down, so negative would probably make more sense. So if I go to the negative, that actually makes more sense. Negative 55 divided by 30 gives me minus 61.4 degrees. Okay, or 300 and what? 18.6, is that right? If you went around and designate it that way. So the final velocity of this is 62.6 meters per second at theta equals minus 61.4 degrees. Okay, good. So as we think of a ball traveling upward in symmetric motion, it starts out with some value in the x direction and a larger value in the y, or some value in the y. It doesn't have to be larger, but in this case I made it that way. When the ball gets to a new point, it will have kept, x will not have changed, but y will be under the acceleration minus 10 meters per second. For each second going up, it's going to slow down. Ball gets to a new point, again, the x will stay the same, but the y will be even less. And then finally, at the apex, it's all in the x direction. But the vectors are symmetric on the way down. So the x stays the same, but the y is headed down at an equal amount of time, falling as it had to rise in the last segment. Again, the x stays the same. The y is fallen until right before it hits. On its way down. Okay? If we were to draw in the vectors there, the vectors would look like that for velocity. This one would be all in the x and then starting to go down like that there. And it would be symmetric on either side. What initial angle will make a projectile go to its highest? Okay, so depending on what angle, how do you get to the highest level? Well, that's not hard. It's just simply going straight up, because if it goes straight up, all the velocity is in the y direction, and that will be, so at 90 degrees, so all velocity in the y direction, it would be in the air the longest. Okay? What angle will make a projectile go the farthest? Well, it turns out that to do that, you'd fire it at 45 degrees. That will maximize your range. What stays in the air the longest? Again, that one's 90 degrees. Oh, I said that already. How about go to the highest point? Also 90 degrees. Now, in terms of landing at complementary angles, um, for trajectories, you can get at complementary, meaning adding up to 90. So if you had one measured at 30 degrees, one measured at 60 degrees, so let's say the 30 degree one, it would go out and then fall, say, over here. It's not in the air as long as the 60 degree one, but turns out that they would land at the same point downrange as long as they're complements of each other. So 60 and 30 would, as would 15 degrees and 75 degrees. Obviously the 75 degree one's in the air longer, but it lands downrange in the x direction, same in the 15 as it does in the 75. Okay, good. Now let's look at some examples for symmetric problems. So say my 11-year-old son kicks a Barbie head, imparting a speed of 14 meters per second at an angle of 30 degrees above the ground. How far does this head go, and how long is it in the air? Okay, so the head is kicked, and at 30 degrees, with a speed of 14 meters per second. And it travels up and comes down at an equal level as it left. Okay. So the question is, how far does the head go? So we're interested in this. And how long is it in the air? Well, to do this, the first part you have to do is you have to find the Vx component and the Vy component of the velocity. And Vx would be the cosine theta, which would be 14 meters per second times the cosine of 30 degrees. Now, I see all the time students will mix that up. They'll put 30 cosine 14. So be careful that you're taking the cosine of angles there. So 14 cosine 30 gives 12.1 meters per second. So that's our Vx. Our Vy, since we're going to break these up and analyze the x and y separately, is 14 meters per second sine of 30 degrees. And since the sine of 30 is 0.5, we get 7 meters per second for Vy. Now we're ready to put our information into a chart. In this case, we use this chart, shrink it a little bit. And in this chart, we have an x, a y up, and a y down. Actually, no. I'm sorry. Forget that. I'm going to do it this way. So we take this chart where we have x and y. We're going to use y up and y down when we do asymmetric in 3.3. So let's think about the x direction. Well, we have the 12.1 meters per second in the x, and that will stay the same throughout. Which makes this 0 and that 0. Do we know anything else in the x? In the y, we know that a is minus 10, and we have this original velocity in the y. The original velocity in the y is 7. But if it's plus 7 going up, the final velocity right before it hits the ground is going to be minus 7 going down. And that's all we know at this point. So I can't fill in either of the ones in the x, delta t or delta s, until I get something else. Until I get delta t in the y. So let's find our average velocity in the y direction. And when we do that, we see that 7 plus a minus 7 is just 0. So we actually have 0 meters per second. And the reason that is because we have speeds going up, or velocities with a positive going up, and velocities that are negative going down. Now, our change in v is vs minus vi, and that will be minus 7 meters per second minus 7 meters per second, which is minus 14 meters per second. That makes sense if we think of it as starting at plus 7 meters per second and ending at minus 7 meters per second. That's a change of minus 14 meters per second. So our delta t in the x direction, or in the y direction, I'm sorry, would be delta v over a, which would be minus 14 meters per second over minus 10 meters per second squared, which is 1.4 seconds. The delta s would be v bar times delta t, but v bar is 0, so we have no delta s, and that makes sense if we have no change in the y, if we have a symmetric going up and coming down. So this delta t here, it will also transfer up to the delta t there. And now we can find out how far it goes. Because delta s is v bar times delta t in the x, so 12.1 meters per second times 1.4 seconds, 12.1 times 1.4, oops, is 16.9 meters. So the question asks, how far does the head go? Well, it goes 16.9 meters. How long is the head in the air? 1.4 seconds. Good. Okay, in World War I, the Germans built a gun called the Paris gun. So named because it shot large 100-kilogram bullets onto Paris. They came out of the barrel at 1,600 meters per second, and the gun was built to fire at approximately 45 degrees. How high did the bullets go, and how far away? So these would travel up and then land some distance away. We're going to assume it's symmetric as it goes. And we're interested in on how high and how far. we know that they leave with an initial speed of 1600 meters per second, and that is at an angle of 45 degrees. Vx and Vy will both be equal because of the 45 degrees, 1600 meters per second, cosine of 45, and 1600 meters per second, sine of 45, and that gives 1,131 meters per second. Okay. So if we have set up a chart like that we had before with the x and y, but since when you ask questions about how high, we're only going to do half of the time that it's in the air to get to its highest point. Okay? So we're just going to do y up, which will make us have to interpret our delta S and the x too. We still have to double it because it will only have gone half that distance by then. But we know what our Vx and our Vy is. 1,131 meters per second. That doesn't change in the x. We know the Vy is initially 1,131, but since we're going to go how high it went, we're going to bring that up to a Vf of 0 meters per second. We know A is minus 10 meters per second squared. So working in the y direction, we can find V bar by adding those two together and dividing by 2, which will give us 565.7 meters per second, and a delta V of minus 1,131 meters per second. Delta T is delta V over A, which gives us 113.1 seconds. Okay? Now, this will give us, we can calculate the delta S, because delta S will be V bar times delta T, or 565.7 times 113.1 seconds, which gives us 63,979 meters into the air. That's how high it goes. Now, to get how far it went, I got to think of the time for a minute. I could either use the same time and double the distance, or I think it makes sense to double the time, since that's really how far. And then we'll get 226.2 seconds. Now I can get how far from V bar delta S times delta T. Oh, I'm sorry. Delta S is V bar times delta T, which is 1,131 meters per second times 226.2 seconds, or 225,832 meters. That's how far. How far and how high So that's about 64 kilometers high and 226 kilometers away. All right, now that ends 3.2.